The broadcast is now starting. All attendees are in listen-only mode.
Hello, thanks for joining me today. The goal for today's webinar is to demonstrate that aging is an important process to understand in formulation science. And since viscosity is a way to measure molecular interactions, we can use viscosity to quantify aging in protein solutions. And stay tuned till the end for some interesting applications data. So first, what we need to do is build the bridge between formulation and viscosity. So to begin, we'll start with the formulation, which is the excipients or osmolytes, depends on which field you're in, what you call those, and the temperature that the formulation is being used in. And these changes in the formulation have a direct influence on the interactions and microstructure in the particles suspended in solution. And these interactions in microstructure can be directly measured by viscosity measurements. And so we can probe at different shear rates. We can shear this fluid at different shear rates, and we can monitor the viscosity changes to get an idea of what's going on in that microstructure. And so what is viscosity exactly? It is a fluid's resistance to flow. It is the forced relative motion between adjacent fluid elements, inducing a non-equilibrium state. And we can think of the shear viscosity as the molecular friction within the fluid. And this will directly reflect the size, shape, and interactions in microstructure of the particles suspended in solution. And in some cases, the viscosity is shear rate dependent. And in these cases, we can probe at different time, or rather length scales, by changing the shear rate. So since shear rate is inverse time, the faster or harder you shear something, the higher the shear rate, the smaller the time scale is that we're looking at. And so on the right here, we just have an example of a homogeneous flow induced by a cone and plate rheometer. We can see that at this interface here, the shear rate is 0, and then it is a homogeneous flow, so the shear rate is the same across the entire length h of this gap here. And so this is just a visual representation of what we're observing. So we can use proteins as colloids as a framework for the interpretation of our modeling or what's going on in our system. And now we can use colloid science, but proteins are complicated particles that don't behave like ideal colloids. But colloid science is sophisticated enough to model protein behavior in solution reasonably well. And in our solutions, the size range of proteins is between 1 nanometer to 1,000 nanometers, or 1 micron. And at this size range, Brownian motion is relevant. So Brownian motion is simply a measure of thermodynamic energy in a solution. The warmer a solution is, the faster the particles diffuse around in solution. And over here on the right, I have a short video clip of a large particle diffusing around randomly under Brownian conditions in a solution. And in our case, since proteins are significantly larger than the solvent molecules on the continuum, so our solvent here is water or buffer, we can call this a pseudo one-component system, just the protein particle floating around, not interacting with these teeny tiny small water molecules. And then we can, with this assumption, we can gauge the interaction potential of the particles that are diffusing around in solution and interacting with each other. And this is really important for aging because, remember, these solutions are dynamic. They are not static. They are diffusing around, interacting, the particles are diffusing around, interacting with each other constantly in a Brownian fashion. And over time, given enough time, these proteins will interact and collide with each other and get stuck together and form clusters and exchange with free-floating proteins in solution. All sorts of interesting dynamic things happen in these solutions as they are stored. And this can cause changes within the fluid structure, which can then be reflected as a change in viscosity. And in many cases, especially with protein solutions, this can be reflected as an increase in viscosity. And so, and we can quantify this pair interaction potential with this expression here, phi over kT, which kT is just thermal energy. And so next, talk about the pair interactions in a microstructure within solutions. These are, again, thermodynamic in nature and are driven by Brownian motion. And so on the left here, we have a plot of the interaction potential as a function of distance, where A is the radius of the particle in solution, and R is the distance between two particles in solution. And this is just a hypothetical particle. Each protein and each formulation in that a protein is dissolved in will have a unique interaction potential curve. And the formulations that we use can alter the interactions, altering this curve, which can then alter the microstructure, which kind of clusters these proteins will form, and change the characteristic length scale of the diffusing objects. And so if we step through this chart, we can kind of see what's going on here. When proteins or particles are very close together, they can be attractive and tend to aggregate. And while they're spread out farther away from each other, they are more repulsive and stabilizing. And as time goes by, again, they're not static, they're dynamic. As time goes by, they collide, they interact, and they can get stuck together. And this whole process is stochastic, which means random. And over time, this stochastic interactions, collisions, exchange of clusters with free protein in solution can cause all sorts of different changes in the fluid structure, but also these large clusters can then collide with other clusters, forming giant aggregates. And over time, aggregation is destined to occur because proteins are metastable in solution. And so what does metastability mean exactly? It means that they're in a state of quasi-equilibrium. Over the time period of our experiments and their use, they'll be stable and behave as expected. But however, as time approaches infinity, as time increases, these proteins will interact and drive towards an equilibrium state or a thermodynamic lowest energy state, which in the case of proteins is aggregation. And we can estimate the time scale that this can occur using the diffusion equation. So this standard 2D diffusion equation where we have diffusivity, time, and then the area length scale that these proteins diffused. And so if you remember that giant yellow particle on my previous slide, this area here is the area that that particle has diffused over this given length scale tau for time. And so remember that this phi over kT on this chart over here is the interaction potential of the protein in solution. And this potential can be altered by changing the formulation that the proteins are suspended in. And so we can look more closely here at phi max and phi min. The contribution of phi max and phi min depends on the charge of the particles. For some colloids, like an ideal colloid, we can have phi max so large that the protein or the colloids will never reach phi min. However, proteins are moderately charged and complicated and not ideal. So the balance between phi max and phi min is extremely important. We can think of phi max as a barrier to aggregation. Will it even aggregate? Will our protein even aggregate? While phi min is more of a measure of the strength of aggregation. Will it aggregate in the time scale that is relevant for our experiment? That's kind of a generalization of what these two parameters mean. When these are in balance, like in the case of proteins, we can observe some interesting phenomena. We can observe reversible clusters, so clusters that form and then one protein in the cluster gets knocked off and then is replaced by another. And then these clusters are aggregates that stay in solution. That's key. So they still participate in the microstructure of the fluid. This we can think of as the influence of phi max, where the individual protein can still participate in cluster formation, and the cluster itself also participates in the solution. Once it has aggregated to a point where it crashes out of solution, it no longer is participating in the dynamics of the fluid. It's no longer taking part. And we can call that an irreversible aggregate. And this irreversible aggregate is the influence of phi min, where it has crashed out of solution and it will no longer participate in the solution. And once out of solution, it stays out of solution. And so we can try and predict this time scale of crashing out or no longer participating in the solution by looking at this equation. And this equation is simply the diffusivity equation just rearranged, and instead of x as our distance, we now have a, because what we're looking at is really, really short distance. We're looking at on the scale of the particle itself. So it's now x has been replaced with a, which is, again, the radius of the particle. And then over on the right here, this exponent, we have the probability of exchange. So this is looking at phi min's influence on the time scale of aggregation. And so this is the probability of attraction, of exchange, and the constant in front is just the length scale divided by the diffusion coefficient, which leaves units of time. And so this is just a kind of an estimate, a guess on how long it will take for these particles to aggregate with each other. So here I have this interaction potential table. This is just a simplified prediction for aggregation, comparing a 100 nanometer particle and a 1 micrometer particle, and different values for phi min over thermal energy. And as you can see that as the interaction potential changes, we get massive changes in the time scale of these events. We can go on the order of milliseconds all the way to the order of years, and this totally depends upon the size of the particles in question as well as their interaction potential. And so there's tons of caveats and nuances to all of this. So bear in mind that proteins have a non-uniform charge and attractive sites and are much more complicated. So diffusing proteins must interact with each other at long enough timescales where they interact in just the right way to induce an aggregation event. And whether this is a clustering or irreversible aggregates, that is completely dependent upon the protein in question as well as the formulation that you use. And this non-uniformity in proteins and protein formulation is yet another reason why protein aggregation and aging is complicated and a difficult to predict process. And so next, I have a pretty cartoon of the aggregation process for people who like pictures, like me. So we have T naught, the initial time point where we've mixed our formulation, all the proteins are separated, distanced out, not interacting. And then we look as time increases to T infinity or T long time, long in the future. It can be years, decades, or it can be hours, seconds. But this is just a simplified speculative cartoon of what's going on in our formulations as they age. So you have our individual proteins, they interact with each other, they form tiny clusters that participate in the structure of the fluid, and these clusters then form larger clusters, reversible aggregates, and again, they're exchanging individual proteins that it's all in motion, all advance, all interacting with each other at the nanometer scale. And eventually, over time, they'll form more aggregates, both reversible and irreversible, and that's when we see precipitates, flocculation, all sorts of other markers of advanced aging in protein solutions. So now I'll step through our viscosity data, but first we need to use some tools in our toolkit, our Rheology toolkit, and we'll start with the zero-shear plateau. So we can investigate these interactions using Rheology. Here on the left, we have an example of an idealized viscosity versus shear rate curve. And on the right here, we have an example of one generated with experiments in-house here at RheoSense with bovine gamma globulin. At low shear rates, we see shear independent viscosity. Now this is called the Newtonian plateau or the zero shear plateau or low shear plateau. Zero shear plateau is an unfortunate name that leads to a ton of confusion. If you remember anything from today's webinar, it's that zero shear plateau does not mean zero shear rate. On our bovine gamma globulin data here, we are on the zero shear plateau and over the shear rates tested here from about 300 inverse seconds to almost 3,000 inverse seconds. And that is definitely greater than zero. So zero shear plateau just means low shear rates or Newtonian plateau. And so next we have this onset of shear thinning at a critical shear rate, which is the onset of non-Newtonian behavior where viscosity is dependent upon shear rate. And this is the power law regime. We observe this in our experimental data with bovine gamma globulin. And then in the idealized case, at really, really high shear rates, we get to another Newtonian plateau, which is often called the infinite shear plateau because it's at very extremely high shear rates that you will observe this behavior. In fact, the shear rates are so high, we can't even get to that plateau region on our instrumentation with bovine gamma globulin. And so as formulations change with age, this chart here will also change. Typically, the zero shear plateau will increase as the formulation changes, but bear in mind there are exceptions. There's exceptions to every rule in biology. Sometimes advanced aging can even lead to a decrease in viscosity, but the key point is that you need to measure your aging process and get an understanding of what's going on with your specific proteins. And so next, we'll go through the data that I collected here at RheoSense. So we began examining the zero shear plateau for signs of aging. We made 250 mg per mil BGG solutions and stored them at 4 degrees Celsius and then measured their viscosity at 25 degrees Celsius. So we began with phosphate buffered saline as our solvent and measured the viscosity at different time points, 1 day after formulation, 7, 14, 28, all the way up to about 2 months at 55 days. And as you can see, that first month, they relatively stayed the same viscosity, but then at day 55, 2 months later, it dramatically increased from 45 centipoise all the way up to about 60 centipoise. We next looked at increasing the ionic strength, so we added 450 millimolar sodium chloride to the formulation, and then tested viscosity over multiple time points over the course of 55 days. And similar to the PBS only buffer situation, the first month they the viscosity was relatively the same, and then at day 55, it increased dramatically to about 85 centipoise. And then we looked at our favorite rheological modifier, arginine, in this case, arginine HCl. And what we noticed is not only were we able to measure the viscosity for longer, up to 92 days after formulation, it also didn't really, the viscosity didn't really change all that much. And in fact, the PBS formulation and the PBS sodium chloride formulation exhibited signs of flocculation, meaning that these visible solid particles of protein had crashed out of solution, these aggregates known as flocks, after 55 days. And once they started flocculating, we couldn't measure them on our instrumentation anymore safely. And so what happens when you throw everything together, put arginine, put high concentration of sodium chloride in an already salty solution? What then? And again, the influence of arginine allowed us to explore aging for a longer period of time. It also didn't change the viscosity over the course of 92 days all that much. And so this data here is just simply the average viscosity data on the zero shear plateau for each formulation tested at each time point. This is just the previous data summarized in a nice, easily digestible bar chart. And we can see the changes in viscosity a little more clearly based on formulation. So here, PBS, we have a maximum increase of about 32.8% between day 1 and day 55. And then with the high ionic strength formulation, that increase bumps up all the way to 41%, so a 41% increase. And then here with our arginine formulation, this change over the course of 92 days was only 20.4%. And then in this case here, the everything case, the change from day 1 to day 92 was only 8%. But if you look at the error bars here, I mean, it basically is no change. It's just an 8% change of the average. And so as you can see, the incorporation of arginine helped prevent age-related increases in viscosity for BGG, or bovine gamma globulin, in solution. With the PBS and the high ionic strength PBS, both increased in viscosity sooner than the arginine-containing formulations and flocculated by day 55, meaning we could no longer measure the solution safely on our instrumentation. These large macroscopic aggregates, flocks, are irreversible aggregates that I mentioned earlier. And these are large enough that you can see them with the naked eye, and they are no longer participating in the solution. We speculate that the reason why we saw this flocculation, this irreversible aggregation early, is that the high ionic strength sodium chloride solution dehydrated the surface of the protein itself, the salting out effect. So when the proteins inevitably interacted and collided with each other, they stuck together more strongly and were unable to participate in exchange in a way that they normally would have, because there's no more water in the way preventing this. And as for the arginine solutions, we think that the arginine has hydrating effect on the protein that is somewhat stronger than the salting out effect from the sodium chloride. I have my email listed later in the presentation, and I would love to discuss with you any ideas that you have about why arginine does the really cool and interesting things that it does. And so, like I mentioned at the very beginning, that I'd have a surprise for people who stuck with me through till the end. And this is aging's impact on injection. Aging not only impacts protein solution storage time, but they also impact their function. Concentrated protein solutions are frequently used as injectable formulations, injectable drugs. And since there can be a delay in formulation used from formulation in the lab or at the manufacturing plant to injection into a patient. Knowing what happens to the injection force as these proteins age becomes pretty important. So here we examined the two most extreme cases, PBS arginine and PBS sodium chloride. And we looked at them at day 1 and day 92 in the case of PBS arginine, and day 1 and day 55 in the case of PBS sodium chloride. And we calculated the injection forces at these shear rates here. So here's some assumptions that we made to calculate the injection force: a needle length of 17 millimeters, inner or needle radius of 0.135 millimeters, and then a piston radius, a piston of the barrel of the needle holding the drug at about 4.325 millimeters. And so looking at these shear rates here on comparing them, this is 3,500 inverse seconds, and over here this is 25,000 inverse seconds, which corresponds to these flow rates here, and results in the following injection forces: about 1.9 newtons in day 1 at the low shear rate, to 13 newtons at the highest shear rate, and then 2.3 newtons at day 92, and 15.1 newtons at the high shear rates. And so this corresponds, the 1.89 to and 2.3, that corresponds to about a 19% increase in injection force, and then this 13 to 15.1 corresponds to about a 16% increase in injection force over the course of 92 days. And then over here, we again looked at these shear rates in question at the PBS sodium chloride formulation. And here again, so that was 2,500 inverse seconds at the low end, and then 26,000 inverse seconds at the high end, corresponds to these flow rates in the needle, corresponds to these injection forces based on the viscosity values you see there. So 2.2 newtons versus 2.8 newtons, and then 20.4 versus 24.7. This is a 26.5% increase in injection force, and this is a 21% increase in injection force over the course of 55 days. So they had a larger increase in injection force over a shorter period of time. The way these aged was dramatically different. And with that, I will be happy to answer any of your questions, and also just thank you for attending this webinar. I look forward to our discussions in the future. Questions? Okay, so let's see. First question: have you seen shear thickening with protein solutions? I have not personally seen shear thickening in protein solutions, in the sense that as you shear a protein, the viscosity increases as the shear rate increases. I've predominantly seen shear thickening. I believe you'd have to get to shear rates much greater than the shear rates that we have the capability of testing in-house to see real shear thinning. And then another question we have here is, should we have studies that last longer than 92 days? I think that's up to, I guess, your own quality and control parameters that you set for yourself. 92 days is 3 months. I would hope that a lot of drugs would be, injectable drugs would be used within 3 months of their formulation at the manufacturing plant, but obviously it's not an ideal world. I would choose your study day lengths based on what you foresee with your own specific formulation. If you think they'll be in storage for 3, 6, 12 months, then you should do stability studies for 3, 6, and 12 months. Another question for storage studies, should we also use temperature studies side by side? I think that's an excellent idea. That's good to know. Which is the most ideal storage condition? Is it refrigeration? Is it freezing? Is it actually room temperature? These are all interesting questions that you can answer by performing tests such as these. So I have another question. If the sample shows yield stress, what would be the effect of aggregation on yield stress? So if this sample shows yield stress, what would be the effect of aggregation? So let me think. That's an excellent question. I guess materials that exhibit yield stress are viscoelastic in nature, and so they are like quasi-fluid, quasi-solid. So aggregation in that case, I could see. Honestly, it could go either way. That I guess the easiest thing for me to answer is measure that yourself on your own instrumentation, because that will give you the best answer. But I would think aggregation in a sample with yield stress would increase the yield stress. Okay, but I will do some digging and get back to you and give you a more satisfying answer when I've done some more reading. Another question, have you correlated your results with zeta potential? No, we have not. However, that would be an excellent thing to look into. When I was a graduate student working with liposomal formulations, used zeta potential all the time to determine how likely a formulation of, in this case, nanoparticles would aggregate. We would test the zeta potential early on and correlate that to, oh, this one will likely aggregate, this one will likely be stable. But no, we haven't compared side by side with zeta potential, but that would be an interesting experiment to do. And then another question, do you guys do sample testing for companies including time-dependent studies? And the answer to that question is yes, we do sample testing, including time-dependent studies for customers. So, yes. All right. So have some. I'll pause for a few more minutes, see if any more questions roll in, and I'll be sure to answer your questions specifically once I do some more background and consult with members of the team. So, all right. Okay, well, I guess that's it for questions. Again, thank you so much for attending the webinar, and I hope you all stay safe, stay healthy, and enjoy your research. Thank you.